All right, let me get the lights and whatnot adjusted, and we're going to go ahead and get started. I don't have an announcement slide today because I kind of want to just jump right into it. Let me make sure I go. There we go. I kind of want to just jump right into it. I will say that I have attendance that I still need to process. I'll get that updated by today. Excuse me. What I'm going to do is, homeworks. I believe homework 6-4 is graded. Homework 7 still being worked on. Obviously, the 3 exams are graded. The only other thing I'll say is make sure that you do the course eval. Again, free free homework points. If you upload proof that you did it, I'll add 10 points to your overall homework average. Okay, so what we're going to do is I've got 3 more problems I'd like to do, and I'll show you them real quick, and then we're going to jump right into it. So I've got our plate problem that I introduced last time, and then I have 2 more problems that I've come up with. This one is just a support reactions problem. It's a little tricky, but again, I think support reactions are kind of an important point to review on the final. And then a moment of inertia problem. So with that, let's go ahead and jump right into this one. So we talked about this one a little bit last time. I'm going to go ahead and, did everybody get the code? All right. I'm going to go ahead and delete this code from the notes for now, but I'll pull it up later. Okay. So we talked about this problem last time, but we didn't have time to really get into it. So what we're going to do is determine the support reactions for this beam. So we've got the support reaction here, here, and then we have our 3 support reactions there. So the first thing I'm going to do is I'm going to start to describe my forces. I'm going to describe my position vectors and my moments. This is an equilibrium problem, which means we're going to need to sum forces and sum moments. Okay? So because we're summing moments, we need to select a location about which to sum moments. And so what I'm going to do is sum moments here. Excuse me. As I would really with any equilibrium problem, I want to try and sum moments at a location where I am eliminating as many unknowns as possible. Okay? So the first thing we ought to do is let's just take the time and describe our forces. Sorry. So we have our reaction vectors. Let me move that down a little bit. Now for A, all I'm going to do is say that that's the magnitude times K. For B, have all 3. Notice that for each of these, they are drawn according to their positive direction. So if we get a negative answer, that just means we assumed a negative direction. C is just that. Okay. Now we have an F vector, a force. Okay. That force is in the negative Z direction. So it's negative 300 times K. That's newtons. We do have a weight. A weight is applied to the middle of the plate. Now, we were told that the plate has a mass of 100 kilograms, but we have to convert that mass to newtons by multiplying by gravity. So weight. So we'll make that negative. That's going to be K. And so that's just going to be negative 981 K in newtons. Now for now, I'm skipping the moment because that's not a force. That is a moment. We will get to that here in a bit. Okay? So now we also need some position vectors. Okay? So position vectors, what I'm talking about, maybe what I'll do is this, is I'll say we needed some F vectors, and we need some R vectors because we're going to be doing R cross F. Now again, I am summing moments at B, so I don't need a position vector for B, but I do need a position vector pointing to A, okay? So for example, we'll say R to A from B. That one's going to be pretty easy because to get from here to here, we go along, let's see, what axis do we go along? We go along the y-axis, and we just go in a distance of 2, but we're going opposite that. So this is negative 2j. We'll say that's in meters. We need an RCB. That's going to be negative 3 because we're going in the opposite direction, and that's in the direction of x, so that's I. We're going to need an R for the force vector. Okay, so to do that, how do we get from, let's see, R to F, or sorry, from B to F? So along the x-axis, we go half the plate, or 1.5. Along the y, we go the whole plate. So that's negative 1/2 I minus 2j. And then lastly, for the weight, we're going to go half and half. So now again, notice how I did not report a vector for the edge, or a position vector for the edge moment. We're going to get to that here in a second. But is everybody with me so far on what I'm doing? Just force vectors and position vectors. So far, so good? Okay, so now what we're going to do is evaluate some cross products. So this will get a little mechanical, so I'll go through the first one. So I'll say so we're summing moments at B. So we don't need to evaluate a cross product for the B vector, but we do for all the others. But fortunately, what we're going to find is that the cross products get a lot easier than you would think. So for example, for the A force, okay, so what we're doing, so if you'll bear me a second, this is going to be MA, the moment generated by that force. Okay, so what we're going to do, so bear with me before you write all this down, but we're going to have I, J, K, and then 0, minus 2, 0, right? And that comes from this vector right here, right? Because there's only a component for the J, 0, 2, 0. And then for the A vector, let me scroll up a little bit so you can see it. The A vector is 0, 0, AZ, right? But what I'm going to do is I'm going to factor out that AZ, and I'm going to say, let's put a 1 here and put the AZ out here. And now this becomes a pretty easy cross product to evaluate. I've got to believe by now we're pretty good at that. Do I need to go through that in detail, or are you okay if I just tell you that the cross product of this is AZ times negative 2I. Is that okay? There's a lot of zeros here. So like, for example, if I knock out the rows and columns, so on and so forth. So for example, for the I term, knock out the rows and columns, get negative 2. For the J term, knock out the rows and columns, I get 0 and 0. K term, knock out the rows and columns, 0 and 0. So the I term is the only term that has a value with it. So far, so good? Okay. Now, we're going to have an RCB crossed with C. That's going to be the moment generated at C. So that's going to be I, J, K. Now the that vector is, let's see, negative 3, 0, 0, and then 0, 0. And instead of CZ, I'm going to put 1 and put the CZ out here. And so when we chug that out, we get CZ times positive 3J. I'm happy to evaluate those cross products if you'd like, but part of this review session is I want you to go through these and see if you're getting the same answer I am. Okay? Now, fortunately, we do have some numerical ones. So we have RF crossed with that force vector. That was a number. Okay? So instead of a variable here, we actually know that the force vector is negative 300. So we could check this one out directly. And fortunately, the math works out pretty nice. We get this. Now the units, let's be clear, are Newton meters. Okay? And lastly, we are going to have our, excuse me, our weight vector bless you. Now we can go ahead and we just put in that weight of negative 981 right here. And so when you chug that out, you get, let's see, 981I minus 1471.5J. And that's what we've got. So now we are ready to start applying static equilibrium, but I do keep putting off this edge moment. Like, what am I going to do with it? Well, let me show you. In general, it's usually easier to deal with your summation of moments first, especially because we are summing moments at a location that eliminates a lot of forces. So you would think that summing moments would be the first step. So let's sort of do that. So we've got MA is, and what did we get up here when we did MA? We got negative 2AZ times I. We have MC, which is 3CZ. Oh, excuse me, that's 3CZ times J. Let's put that over here. So we've got MF, which is 600 times I minus 450, or plus, here, let's do it like this. Group our signs together. We have MW, which is 981I plus negative 1471.5 J. And now I'm going to deal with this edge moment. But the problem is I haven't developed an edge vector yet. So how do I do that? Well, let's go back to the problem. What I am saying is that I have a 200 Newton moment edge moment, or 200 Newton, a 200 Newton meter moment. applied on the edge of this plate. And notice that the direction in which it's going. How do I know, first off, what axis that's aligned towards, and whether or not that's a positive or negative moment? The answer is to use an incredibly bad amount of sketching and to use the right-hand rule, okay? Notice how if my thumb points in the direction of the y-axis, that I am pointing along the axis about which this moment is rotating. And notice how the moment is also rotating opposite the direction of my finger. See, the moment's going like this. But if I point my thumb in the positive y direction, the moment's going in the opposite direction. So the answer is that this vector is negative 200 j. That is how we describe that edge moment. And all we do is we just add that edge moment to all the summation of moments down here. So it's just negative 200 j. It's that simple. Does that make sense? You don't do an R cross F for that because it's already a moment. You just add it to all the other moments that you've already computed. So now what we can do is we can recognize that this column of values is the sum of the moments about the x-axis, and this column of moments is the sum of the moments about the y. So if I sum moments, let's say about the x-axis, I'm going to get negative 2az plus 600 plus 981 equals 0. I could solve that pretty easily and get az is 790.5 newtons. If I sum moments about the y, just all those coefficients, all right, all those are newtons, but Newton meters, but I'll just leave that off. So 3CZ minus 450 minus 1471.5. Let me put a decimal there, make sure that's really clear. Minus 200 equals 0. Solve for CZ. I get CZ is that. And those are the unknowns that I get from summing moments. You can get rid of that line because I don't think that really matters at that point. If we now consider summing forces, remember this is an equilibrium problem, so we know that the sum of those forces must be 0. Put a vector over that 0. So what all forces do we have in this problem? Well, we've got the reactions, A, B, and C. We've got the force vector and the weight. Remember, the edge moment is a moment. It's not a force. We have A, B, C, F, W. Now, if you remember, B was the only one that had 3 components. The rest only had a component in the the z direction. Now A was AZ times K, but we just figured out what AZ was. AZ is 790.5. CZ is 707.2. F was minus 300. And this is minus 981. So again, column by column, summing forces in the X, we find that BX is 0. Summing forces in the Y, we find that BY is 0. It's only summing forces in the Z, or along the Z-axis, we actually get a value for BZ. And this is the only one where our assumption was incorrect. Because if you look at that, you can see the BZ's probably got to be negative in order for that equation to be 0. And if you guess that, you would be right. Lumping everything all over to the other side, you get that BZ is 216 or negative 216.7. And that's the problem. Again, I think that is a way more difficult problem and a way longer problem than you could expect on the exam. But there's so much that's packed into that one problem in terms of cross products, identifying reactions, strategy, what your goal is at the end, so on and so forth. Does anybody have any questions about this problem? And don't let me interrupt if you've got questions about the final itself, okay? I really want to make sure that I'm addressing any lingering questions you have about the exam. Everybody good? Okay. Now, I really like this next problem because this next problem covers, this is one that I really am concerned that we fully get right. Just a support reactions problem, that's it. But if there was any one thing that messed everybody up on the last exam, it was the reactions. It really wasn't the construction of the shear and moment diagrams or the analysis of trusses. It was the reactions necessary to get to there. And this is a weird problem, but I guess my point is it's really not. It's no different than any other problem, okay? It looks bizarre, it looks strange, but this is a reactions problem like any other, okay? And so I want to make sure that we're developing a systematic approach to handling these types of situations, okay? So I have a frame that's subjected to a series of loads. I've got a 12 kip load here, a 20 kip load here, and a distributed load. Before we do anything, let's talk about that distributed load. I need to take that distributed load and collapse it into a point load. How much is the point load going to be? If it's 2 kips per foot over a distance of 6 feet, what is that? 12 feet, 12 kips. And how far from this left edge is that going to be? No, from where I've drawn right here, what's this dimension? 3. The arrow's in here. Okay. Now what I'm going to do is I'm going to identify my unknown reactions. How many unknown reactions do I have at B? 1. It is a vertical reaction, and so I am going to assume that that reaction is acting upwards. How many unknown reactions do I have at A? 2, okay? I'm going to assume that the vertical reaction is also upwards, So we'll call that AY. What about the horizontal reaction of AX? What direction do you think I ought to assume that a reaction is going to be? To the left. And probably the reason that you're saying that is because of that 12 kips. Okay? Because if I summate forces in the x direction, assuming forces to the right are positive, looking at the entire structure, I ignore that, I account for that, but I ignore this, and this. That's what I meant to say. So these three forces over here on the right are all vertical, so I ignore them. All I have is an AX acting to the left and a 12 kips acting to the right. So if this is negative AX because I've drawn it to the left, and this is positive 12 kips because I've drawn it to the right, that means that I assumed correctly, and AX is in fact 12 kips acting to the left. That is one of the answers right there. The AX is 12 kips to the left. Does everybody see that? Yes, sir.
There's only two types of supports you should worry about for the final.
And fixed supports, but nothing else. Fixed supports are basically, the only difference between this and a fixed support is a fixed support also has a moment reaction. But these are more important. Much more important. At least for the contents or the context of this final. Simply because these types of supports are going to be prevalent in both trusses and beams. You're not going to see a fixed support on a truss because there's no moments in a truss. Okay. Now what I'm going to do now is I've got two remaining unknowns. I've taken care of this. I've got an unknown here and an unknown here. So I'm going to summate moments. And typically what I like to do is sum moments at a location where a lot of my forces intersect. So I'm going to sum moments at A. All right, and I'm going to do that down here because that equation might get a little long. Let's sum moments about the A support and see what By needs to be in order for them to equal 0. So if I'm summing moments at A, I do not consider AX and AY. Okay? Does this 12 kips generate moment at A? Yes. Is it positive or negative moment according to my assumed sign convention? Positive. What is the moment arm? Say it again. Well, it's 4. The moment arm is 4, so 12 times 4 is 48. I'm talking about the distance, the moment arm. The moment arm is 4 feet, right? Okay? I want to make sure that's clear, okay? So this is positive 12 kips times 4 feet. Let's take it one step at a time, all right? Now, 20 kips, does that generate moment at A? Yes, okay? Is it positive or negative moment according to our sign convention? Negative. What is the moment arm? 3 feet. Hello? I can't get too upset. That's happened to me before. Okay. Does this distributed load generate moment at A? Yes. Is it positive or negative moment according to our sign convention? Negative. Now, what is the moment arm from A? 6 feet. It's not 4 feet, it's 6 feet. It's the shortest distance from the line of action to the point in question. So it is minus 12 kips times 6 feet. Now, does By generate moment at A? Yes. Is that positive or negative moment according to our sign convention? Positive. And what is the moment arm? How far is the moment arm from A? 11 feet. So this is, as you were saying, 48 foot kips. So 48 minus 60 minus 72. So 84 divided by 11, it's a negative and a negative, so that the signs are going to cancel. That's going to be positive, and it's 7.64 kips. So that's 7.64 kips going up. All right. And then lastly, stemming forces in the y direction, I now account for everything that's vertical on this problem, everything. So for my reactions, I got AY and BY going up. And for my loads, I got 20 and 12 going down. I now know, sorry. I now know what BY is. Let me stop for a second, let everybody digest this a bit. I know we've been going pretty quick for the very last class in Engineering 213, right? I didn't hear anybody. Oh, thank God. 8 o'clock in the morning. I've had it with you, Dr. Mike. I'm done. I'm kidding. Maybe I'm not. I don't know. All right. Let me stop for a sec. Did this make sense? Does anybody have any questions about this? If you can do this problem, I think you can do just about any support reaction computation on the exam. Anything you would get on the exam is going to be much easier, in my opinion, than this. Any questions? Y'all need any more time to copy this down? Or? All right. So I did have one more problem for you. I think it's a good review of centroids as well as moments of inertia. So what we're going to do is determine the centroidal moment of inertia about the x-axis for the shape shown, right? So imagine this is a T-beam that we're bending up and down, and so we're trying to find out how stiff it is, okay? So in order to do that, we need to find the location of the centroid up and down. Keep in mind the shape is symmetric, so we know where the centroid is this way. We want to know where the centroid is this way. And there is a key value that I am interested in you making sure that you can identify in this problem, but we'll get to that here in a second. Now, what I'll do is I will go ahead and place a arbitrary coordinate system for our reference. I can do better than that. That's an arbitrary coordinate system for our reference. Really what I need to find, or what I need to do is ensure that I am referencing everything from the centroid of the shape in question. Now, to reference everything appropriately, let's put some numbers to this. We'll call that shape 1 and call this shape 2. So shape 1 is this lower flange. Shape 2 is this upper stem or this upper web. Now, you know how we do moment of inertia calculations or centroid calculations. We do it all as in one big table. So we're going to have two shapes. and then a summation column at the bottom. So the first thing that we'll do is record the areas. I gotta believe that's pretty easy. Shape 1, these are all rectangles, so 12 times 2, that's 24. And 14 times 3 is 42. So if I sum that up, 66. All right. This column, I really want you all to pay attention to. This column was the single biggest mistake on the Centroid problem on exam 3. I want everybody to pay attention. This is important. When we compute the location of a centroid, we compute it from a common reference location. In this case, we are expressing distances from our origin, or in this case, from the bottom of the shape. So what I need to do is I need to locate the centroid of each of these little rectangles and express it from the bottom. So question, how far is it from the bottom of the entire cross-section, that little plus right there? 1. How far is it from the bottom of the cross-section to that? 9. I cannot tell you how many people on exam 3 looked at that and said 7. It's not 7, it's 9. It's from the bottom, okay? When we compute a weighted average, that weighted average needs to be expressed from a common reference location, okay? So that goes from here, we go 2, and then half that, so 7. So like this value right here is probably like the most important value in the entire calculation. If you understand that, you understand centroids. Because some of the problems on the exams, like I would see all these like triangles and circles, and all the centroids would just be like 1 or 1.5. It's like, no, it's got to be from the origin. It should be like 7 or 7.5 or something like that. All right, so 24 times 1, 24. 42 times 9, 378. So you sum those up, 402. And down here, we can compute y bar. Just looks suspiciously like a 6. So that ends up being something like 6.091 inches. All right. Now, let me move this up a little bit. We do need to compute the moment of inertia of each of the rectangles. Does anybody remember what is the moment of inertia of a rectangle? Does anybody remember that formula? BH cubed over something. 12.
You need to memorize those?
No, any of those lookups you will be given. Now, let me say, it's probably not the worst idea in the world to, kind of know them offhand. I mean, it'll give you a competitive edge, I'll say, but do you need to memorize them? No. Trying to reorganize this a little bit. Okay, that's better. All right. So now, B in this case, let's be clear, B is the width along the x-axis. I'm doing along the x-axis. H is the height along y. Okay? So what that means is for shape 1, it's 12 times 2 cubed over 12, so it's a really small number. It's only 8. But for this shape, it's 3 times 14 cubed over 12. So it's 686. After this, the problem is incredibly algorithmic. Like at this point, it should just be you just sort of chug it out. There's nothing that you really need to interpret. You just sort of do it. So the first thing that you do is you compute your D values, but that's just, sorry, hold on. Your D values are just your Y values minus Y bar. So you just take 1 minus 6.091, so negative 5.091, and this one is positive 2.909. It doesn't matter which direction that you do the subtraction, because your final calculation is to use the parallel axis theorem where you're going to square those values anyways. So I plus AD squared, so 8 plus 24 times that squared. So when you chug that out, you should get something like 630.02, and this one you should get 1041.44. And I think when you sum that up, 1671.5. So your moment of inertia is that. I'll tell you though, again, I think the most important value in this entire problem is that. The answer is not 7, it's 9. If you get that, if you understand that, that should be really the most difficult part on the exam, or for that problem. All right, I'm going to stop for a sec, let everybody catch up. Have these past couple days been beneficial, as opposed to me just standing here going, all right, what are the questions? I figure let's just do something, right? Before we close this up, I want to see if anybody has any questions about this problem. Yes, sir.
About that problem, I just want to make sure we get a formula sheet for the final, right?
Yeah. Self-made, put whatever you want on it except for fully worked out problems, and don't just fully screenshot slides. So, same as all the others. All right. Let me mention a couple quick housekeeping items, and then we'll close up shop. So, number one, I'll get the attendance grades posted by the close of business probably today. I will upload the grades to the attendance probably by close of business today. I'll upload the video hopefully as quick as possible. A couple other things. We're still working on grading homework, but everybody has the at-home spreadsheet, so you can sort of game out your final exam grade. I will get the course evals graded if you submit them. Please do them. It really does help out. And I guess I'll see you bright and early for the final. And I do want to say, I know that it has been trying walking across campus at 8 o'clock in the morning to Corbley Hall, far away from our home on the other side of 3rd Avenue. But it's been fun. This is certainly the largest statics course I've ever taught. I've taught Engineering 103, but I don't know that you consider that like a class like this. But it's been fun. For you mechanical and biomedical engineers in the room, there is a chance this is the last time that we see each other as a, from a professor to student standpoint. While I'm your associate dean, I probably might, or I might not be having you in class much anymore. So if I don't, I do wish you the best throughout your academic career. For you civil engineers, sorry, you're gonna have to get to know me a little bit better. Shucks. But it has been, I know that this is really sort of your first real foray into engineering, and I know this can be a challenging class, but I do want to say I'm proud of all of you. I will see you all Monday morning at 8 a.m. for your last celebration in Engineering 213. That's all I have, everybody. I'll pull up the QR code again, but I will see you all on Monday.